Good day everyone, I'm Roldan David, your reporter for Chapter 21 Data and Computer Communications. This chapter talks about Internetwork operation. We have a quote for this chapter. We are beginning to understand, or at least to appreciate, the cause of time delays and overloading phenomena in communication systems, handling competing users with different level of importance. There's a basis for hope that one day we will be able to automate highly sophisticated priority systems. Such systems may even be so effective as to provide the operational equivalent of exercised judgment. This chapter begins with a discussion of multicasting. Next, we look at a new approach to managing internet traffic known as Software Defined Network or SDN and the related protocol OpenFlow. The chapter then introduces the topic of mobile IP. Multicasting. Typically, an IP address refers to an individual host on a particular network. IP also accommodates addresses that refer to a group of hosts on one or more networks. Such addresses are referred to as multicast addresses, and the act of sending packets from source to members of multicast group is referred to as multicasting. It is the act of sending a packet from source to the members of a multicast group. Multicast addresses that refers to a group of hosts on one or more networks. It has a number of practical applications. For example, we had multimedia. A number of users tune in to a video or audio transmission from a multimedia source station. Next is that teleconferencing, a group of workstations from a multicast group such that a transmission from any member is received by all other members. And we also have database. All copies of replicated file or database are updated at the same time. And second to the last is the distributed computation. Intermediate results are sent to all participants. And lastly, the real-time work group. Files, graphics, and messages are exchanged among active group members in real time. So, we proceed to the LAN multicast. LAN multicast is easy. Send to IEEE 802 multicast address. Those in multicast group will accept it. Only a single copy of packet is needed. A transmission from any one station is received by all other stations on LAN. Multicasting done with the scope of a single LAN segment is straightforward. IEEE 802 and other LAN protocols include provision for MAC level multicast addresses. A packet with a multicast address is transmitted on a LAN segment. Those stations that are members of the corresponding multicast group recognize the multicast address and accept the packet. So we have this example configuration in figure 21.1. In this case, only a single copy of packet is ever transmitted. This technique works because of the broadcast nature of a LAN. A transmission from one station is received by all other stations on the LAN. In an internet environment, multicasting is a far more difficult undertaking. To see this, consider the configuration of of this example, a number of LANs are interconnected by routers. Routers connect to each other either over high-speed links or across a wide area network such that network 4. A cost is associated with each link or network in each direction, indicated by the value shown leaving the router for that link or network. Suppose that the multicast server on network N1 is transmitting packets to a multicast address that represents the workstations indicated on networks N3, N5, and N6. Next is the multicast strategies. We have these three: broadcast packet to each network. If server does not know members of group, it requires certain packets. Could send multiple unicast packets to each network with members in multicast group. It requires 11 packets. And the true multicast were spanning tree replicated by routers at branch points, and it requires 8 packets. Next, as the table 21, traffic generated by various multicasting strategies. This table summarizes the number of packets generated on the various links and networks in order to transmit one packet to a multicast group by this method. In this table, the source is the multicast server on network 1. In figure 21.1, the multicast address includes the group members N3, N5, and N6. So let's proceed for the multicast transmission example, the figure 21.2. In figure 21.2a shows the spanning tree for transmissions from the source to the multicast group, and on the other hand, in figure 21.2b shows this method in action. The source transmit a single packet over N1 to router D. D makes 2 copies of the packet to transmit over link 3 and link 4. B receives the packet from link 3 and transmit it to network 3, where it is read by members of the multicast group on the network. Meanwhile, router C receives the packet sent on link 4. It must now deliver the packet to both E and F. If network N4 were a broadcast network like an IEEE 802 LAN, then C would only need to transmit one instance of the packet for both routers to read. If N4 is packet switching 1, then C must make 2 copies of the packets and address 1 to E and 1 to F. Each of the routers in return retransmits the received packet on N5 and N6 respectively. This table shows the multicast technique requires only 8 copies of packets. So here's the requirements for multicasting. Router may have forward more than 1 copy of packet. Need convention to identify multicast addresses. IPv4, class D, IPv6. Nodes translate between IP multicast addresses and list of networks containing group members. Router must translate between IP multicast address and network multicast address. In ordinary unicast transmission over an internet in which An ordinary unique transmission over an internet in which each datagram has unique destination network. The task of each router is to forward the datagram along the shortest path from the router to the destination network. With multicast transmission, the router may be required to forward two or more copies of an incoming datagram. In our example, routers D and C both must forward two copies of a single incoming datagram. Thus, we might expect that the overall functionality of multicast routing is more complex than unicast routing. The following is a list of required functions. A convention is needed for identifying a address. Is a needed multicast address in IPv4 class D addresses are reserved for this. Suppose these are 32-bit addresses with 1110 as their high order 4 bits, followed by a 28-bit group identifier. In IPv6, a 128-bit multicast address consists of an 8-bit prefix of all ones, a 4-bit flags field, a 4-bit scope field, and a 112-bit group identifier. The flags field currently only indicates whether this address is permanently assigned or not. The scope field indicates the scope of applicability of the address, ranging from single network to global. Second is each node, router, or source node participating in the routing algorithm must translate between an IP multicast address and the list of networks that contain members of this group. This information allows the node to construct a shortest path spanning tree to all of the networks containing group members. A router must translate between an IP multicast address and the network multicast address in order to deliver a multicast IP datagram on the destination network. For example, in IEEE 802 networks, a MAC level address is 48 bits long. If the highest order bit is 1, then it is a multicast address. Thus, for multicast delivery, a router attached to an IEEE 802 network must translate a 32-bit IPv4 or a 128-bit IPv6 multicast address into a 48-bit IEEE 802 MAC level multicast address. So let's continue. The mechanism required for host to join leave multicast. Routers must exchange information which networks include members of given group. Sufficient information to work out shortest path to each network. Routing algorithm to calculate shortest path. Routers must determine routing paths based on source and destination addresses. Although some multicast addresses may be assigned permanently, the more usual case is the multicast address are generated dynamically, and that individual hosts may join and leave multicast groups dynamically. Thus, a mechanism is needed by which an individual host informs router attached to the same network as itself of its inclusion in and exclusion from a multicast groups. IGPM described subsequently provides this mechanism. And routers must exchange two sorts of information. First, routers need to know which network include members of a given multicast group. Second, routers need sufficient information to calculate the shortest path to each network containing group members. These requirements imply the need of multicast routing protocol. A discussion of such protocols is beyond the scope of this book. A routing algorithm is needed to calculate shortest paths to all group members. Each router must determine multicast routing paths on the basis of both sources and destination addresses. So next is the figure 21.3, spanning tree from router C to multicast group. When RC receives a packet with such a multicast address, that packet is already intended for network 3, 5, and 6. It is the shortest path to each of these three networks and produces the shortest path spanning tree shown in figure 21.3. As a result, router C sends two copies of the packet out over network 4, one intended for N5 and one intended for N6, but it is also sends a copy of packet to router B for delivery on network 3. Thus, router B will receive two copies of packet, one from RD and one from RC. This is clearly not what was intended by the host on N1 when it launched the packet. To avoid unnecessary duplication of packets, each router must route packets on the basis of both source and multicast destinations. So next is the Internet Group Management Protocol. It defined in RFC 3376, used to exchange multicast group information between hosts and routers on a LAN. Hosts send messages to routers to subscribe and unsubscribe from multicast group. Routers check which multicast group are of interest to which hosts. IJMP currently at version 3. So next is the operation of IJMP V1 and V2. IJMP V1 host could join group. Routers use timer to unsubscribe group members. IJMP V2 enabled hosts to unsubscribe. Operational model. Receivers have to subscribe to groups. Sources do not have to subscribe to groups. Any host can send traffic to any multicast group. And the problems: spamming of multicast groups, establishment of distribution trees is problematic, and finding globally unique multicast addresses is difficult. And here's the IGMP v3. Addresses weaknesses by allowing hosts to specify a list from which they want to receive traffic, blocking traffic from other hosts at routers, allowing hosts to block packets from sources that send unwanted traffic. So let's proceed to figure 21.4, IGMP v3 message formats. So this is the format. A, the membership query message. All IGMP messages are transmitted in IP datagram. The current version defines two message types: membership query and membership report. Membership query message is sent to multicast router. There are three subtypes. A general query used to learn which groups have different have members on the attached network. A group specific query used to learn if a particular group has any members in attached network, and a group and for source specific query used to learn if any attached device desires reception of packets sent to a specified multicast address from any of a specified list of sources. So the format has the following fields, or consists the following fields. First is the type. It defines this message. This defines this message type. And we have max response code. It indicates the maximum allowed time before sending a corresponding report in units of 1/10 second. Next is the checksum, an error detecting code calculated as the 16-bit once complement addition of all the 16-bit words in the message for purposes of computation. The checksum field is itself initialized to a value of 0. This is the same checksum algorithm used in IPv4. Group address 0 for a general query message, a valid IP multicast group address when sending a group specific query or group and source specific query. And we also have S flag when set to 1 indicates to any receiving multicast routers that they are to suppress the normal timer updates they perform upon hearing a query. And then the QRV, or querier's robustness variable. If non-zero, the QRV field contains the RV value used by the querier. Example, the sender of the query. Routers adapt the RV value from the most recently received query as their own RV value, unless that most recently received RV was 0, in which case the receivers use the default value, or statically configured value. The RV dictates how many times a host will retransmit a report to assure that it is not missed by any attached multicast routers. And then we also have the QQIC, the querier interval code, specifies the QI value used by the querier, which is a timer for sending multiple queries. Multicast routers that are not current querier adapt the QI value from the most recently received query as their own QI value, unless that most recently received QI was 0, in which case the receiving routers use the default QI value. And we also have the number of sources, specifies how many source addresses are present in query. This value is non-zero only for a group and source specific query. And lastly, the source addresses. If the number of sources is n, then there are in 32-bit unicast addresses appended to the message. And next is also the figure 1.4 IGMP v3 message formats, which is the B membership report message. It has fewer it has fewer following fields or consists following fields. It only has the type defines this message type, and the checksum, an error detecting code calculated as 16-bit ones complement addition of all 16-bit words in the message. And then the number of group records specifies how many group records are present in this report. And lastly, the group records. If the number of group records is m, then there are m 32-bit unicast group records appended to the message. Next is the C group record. These are the following fields. The record type defines this record type as described subsequently. The aux data length of auxiliary data field in 32-bit words. Number of sources specifies how many source addresses are present in this record. Then we have the multicast address, the IP multicast address to which this record pertains. Source addresses. If the number of sources is n, then there are n 32-bit unicast addresses appended to the message. Auxiliary data, the last one. It is an additional information pertaining to this record. Currently, no auxiliary data values are defined. So let's proceed to the IGMP operation joining. IGMP host want to make itself known as a group member to other hosts and routers on LAN. IGMP v3 can signal group membership with filtering capabilities with respect to sources. These are the exclude mode and all members except those listed, and include mode only from group members listed. To join a group, host sends an IGMP membership report message. Address field is multicast address of group sent in an IP datagram with the same multicast destination address. Current group members receive and learn new member. Routers listen to all IP multicast addresses to hear all reports. So next, where's the IGMP operation keeping list valid. To maintain a valid current list of active group addresses, a multicast router periodically issues an IGMP general query message sent in an IP datagram with all hosts multicast address. Each host that still wishes to remain a member of one or more multicast groups must read datagrams with the all host address. When such a host receives the query, it must respond with a report message for each group to which it claims membership. Note that the multicast router does not need to know the identity of every host in a group. Rather, it needs to know that there is at least one group member still active. Therefore, each host in a group that receives a query sets a timer with random delay. Any host that hears Another host claim membership and the group will cancel its own report. If no other report is heard and timer expires, a host sends a report. With this scheme, only one member of each group should provide a report to the multicast router. Then next is the group membership with IPv6. IGMP defined for IPv4 uses 32-bit addresses. IPv6 Internet needs functionality. IGMP functions included in Internet Control Message Protocol v6, ICMP v6. ICMP v6 has functionality of ICMP v4 and IGMP. ICMP v6 includes group membership query and group membership report message. When a host leaves a group, it sends a leave group message to the all routers static multicast address. This is accomplished by sending a membership report message with the include option and the null list of source addresses. IGMP was defined for operation with IPv4 and makes use of 32-bit addresses. IPv6 internets need the same functionality rather than to define a separate version of IGMP for IPv6. Its functions have been incorporated into the new version of the Internet Control Message Protocol, or the ICMP v6. ICMP v6 includes all the functionality of ICMP v4 and IGMP. For multicast support, ICMP v6 includes both as said above, which are used in the same fashion as in IGMP. So let's go back here on IGMP operation. The leaving host leaves group by sending leave group. Next is the PIM, the protocol independent multicast, a separate routing protocol independent of any existing unicast routing protocol, and designed to extract needed routing information from any unicast routing protocol. It recognizes that a different approach may be needed to multicast routing depending on the concentration of multicast group members. It defines two modes of operation, the dense mode and the sparse mode, which will be tackled in the next slide. Here, dense mode, appropriate for intra-autonomous system multicast routing, may be viewed as a potential alternative to a multicast version of OSPF known as IMOSPF. Sparse mode, suited for inter-autonomous system multicast routing. RFC 2362 is defined as a group in which the number of networks domains with group members represent and significantly smaller than the number of networks domains in the internet. The internet spanned by the group is not sufficiently resource rich to ignore the overhead of current multicast routing schemes. So next is the figure 21.5 example of PIM operation. The approach taken for spur smooth PIM has the following elements. For multicast group, one router is designated as rendezvous point or the RP. A group destination router sends a join message toward the RP requesting that its members be added to the group. The requesting router uses a unicast shortest path route to transmit the message toward the RP. The reverse of this path becomes part of the destination tree from this RP, the listeners in this group. Any node that wishes to send a multicast group sends packet toward the RP using a shortest path unicast route. This figure 21.5 illustrates the sequence of events once the destination begins to receive packets from the source by the shortest path router. It sends prone packets from that source to this destination. The destination will continue to receive multicast packets from other sources via the RP-based tree unless and until it prunes those sources. Any source router must continue to send multicast packets to the RP router for delivery to other multicast members. The selection of RP for a given multicast group is a dynamic process. The initiator of the multicast group selects primary RP and small ordered set of alternative RPs. In general, RP placement is not a critical issue because the RP-based tree will not be used for most receivers after shortest path routers are followed. So let's proceed to the evolving network requirements. Increasingly widespread use of server virtualization makes it possible to partition a single machine into multiple dependent servers. Conserving hardware resources also makes it possible to quickly migrate a server from one machine to another for load balancing or for dynamic switchover in the case of machine failure. It has become a central element in dealing with big data applications and implementing cloud computing infrastructures. Increasing use by employees of mobile devices such as smartphones, tablets, and notebooks to access enterprise resources. Network managers must be able to respond rapidly. Next is the figure 21.6 is the illogical structure. The figure 21.6 illustrates the logical structure of an SDN. Central controller performs all all complex functionality including routing, naming policy, declaration, and security checks. This constitutes the SDN control plane and consists of one or more SDN servers. SDN is a software-defined networking. It is a new SDN network architecture that comprises different network technologies to build flexible, scalable, agile, and easy manageable networks. SDN does this job by separating control and forwarding planes. The application plane is the layer that has applications and services that make requests for network functions from the control plane and the data plane. And the API is the application programmable interface. It provides system and software interaction. Then the middle one is the control plane. In routing, control plane refers to all functions and processes that determine which path to use to send and the packet or frame. Control plane is responsible for populating the routing table, drawing network topology, forwarding table, and hence enabling the data plane functions. Means here the router makes its decision. In a single line, it can be said that it is responsible for how packets should be forwarded. And we also have the open flow as the first standard communications interface defined between the control and forwarding layers of an SDN architecture. OpenFlow allows direct access to and manipulation of the forwarding plane of network devices such as switches and routers, both physical and virtual. And the data plane, in routing, data plane refers to all the functions and processes that forward packets or frames from one interface to another based on control plane logic. Routing table, forwarding table, and the routing logic constitute the data plane function. Data plane packet goes through the router and the incoming and outgoing of frames are done based on control plane logic. Means in single line, it can be said that it is responsible for moving packets from source to destination. It is also called as forwarding plane. So let's proceed to the SDN domain structure. In large enterprise network, the deployment of a single controller to manage all network devices would prove unwieldy or undesirable. A more likely scenario is that the operator of a large enterprise or carrier network divides the whole network into a number of non-overlapping SDN domains. Source the SDN domains. Reasons for using SDN domains: the scalability, privacy, incremental deployment. In scalability, the number of devices an SDN controller can feasibly manage is limited. A reasonably large network may need to deploy multiple SDN controllers. In privacy, a carrier may choose to implement different privacy policies in different SDN domains. And thus, in the incremental deployment, a carrier's network may consist of portion of legacy and non-legacy infrastructure. Dividing the network into multiple individually manageable SDN domains allows for flexible incremental deployment. Let's proceed for Destiny. Protocol being developed for interfacing SDN domain controllers. Functionality includes coordinate flow setup originated by application continuing information such as path requirement, and service level agreements across multiple SDN domains. Exchange reachability information to facilitate inter-SDN routing. Message type tentatively include reachability update, flow setup, tear down, update request, capability update. And then the next is the open flow. Defined in OpenFlow switch specification published by the Open Networking Foundation (ONF). ONF is a consortium of software providers, content delivery networks, and networking equipment vendors whose purpose is to promote software-defined networking. It's both a protocol between SND controllers and network devices and a specification of the logical structure of the network switch functionality. To turn the concept of SND into practical implementation, two requirements must be met. There must be a common logical architecture in all switches, routers, and other network devices to manage by an SDN controller. Second is it should have a standard secure protocol is needed between the SDN controller and the network device. And then it is the figure 21. It's all about the open flow switch. This figure 21.8 illustrates the basic structure of the open flow environment as an SDN controller communicates with OpenFlow compatible switches using the OpenFlow protocol running over the secure sockets layer or SSL. Each switch connects to the other OpenFlow switches and possibly to end user devices that are the sources and destinations of packet flows. Within each switch, a series of tables, typically implemented in hardware or firmware, are used to manage the following of packets through the switches. Next is the tables. A flow is a sequence of packets traversing a network that share a set of header field values. The open flow specification defines three types of tables in the logical switch architecture. The flow table matches incoming packets to a particular flow and specifies what functions are to be performed on the packets. There may be multiple flow tables that operate in pipeline fashion. Next one is the group table. May trigger a variety of actions that affect one or more flows. Lastly, the method table can trigger a variety of performance-related actions on a flow. The open flow specification Next is the flow table components. Basic building block of logical switch architecture. It may include a table miss flow entry, which wildcards all match fields regardless of value and has the lowest priority. Contains entries consisting of 6 components. First is the match field, used to select packets that match the values in the field. And then the relative priority of table entries. And the counters, updated for matching packets. The OpenFlow specification defines a variety of timers. Examples include the number of received bytes and packets per port, per flow table and per flow table entry, number of dropped packets and duration of flow. Next is the instructions, actions to be taken if a match occurs, and then the timeouts, maximum amount of idle time before a flow is expired by the switch, and lastly the cookie, opaque data value chosen by the controller, may be used by the controller to filter flow statistics, flow modification, and flow deletion, not used when processing packets. A flow table may include a table miss flow entry, which all fields, which wildcards all match fields. So next is the match field components. It consists of the following requirements. Required fields which must be supported by any OpenFlow compliant switch. The ingress port. Ingress port is the identifier of the port on this switch on which the packet arrived. This may be physical port or switch defined virtual port. The Ethernet source and destination addresses. Each entry can be an exact address, a bit mask value for which only some of the address bits are checked, or wildcard value, match any value. Next is the IPv4 or IPv6 protocol number. Each entry can be exact protocol number value indicating the next header in the packet. IPv4 or IPv6 source addresses and destination addresses. Each entry can be an exact address, a bit mask value, a subnet mask value, or a wildcard value. The TCP source and destination ports, and the UDP source and destination ports. The following fields may be optionally supported. The physical port. It is used to designate underlying physical port when packet is received on a logical port. The metadata, additional information that can be passed from one table to another during the processing of packet. It is discussed subsequently. The Ethernet type field, VLAN and VLAN user priority. Fields in the IEEE 802.1q virtual LAN header. The IPv4 or IPv6 DEs and ECN. The SCTP source and destination ports. The ICMP type and code fields. The ARP opcodes. The source and target IPv4 addresses and ARP payload, On the IPv6 flow label, the ICMPv6 type and code fields, the IPv6 neighbor, discovery source and target addresses, and lastly, the MPLS label value, traffic class, and BOS. Next is the instruction component. Consists of a set of instructions that are executed if the packet matches the entry. Actions describe packet forwarding, packet modification, and group table processing operations. The OpenFlow specification includes the following actions. The output, forward packet to a specified port. Set queue. Set queue. Sets the queue ID for a packet. When the packet is forwarded to a port using the output action, the queue ID determines which queue attached to this port is used for scheduling and forwarding. The packet forwarding behavior is dictated by the configuration of the queue and is used to provide basic quality of service support. And in the group, process packet through specific group. Push tag and pop tag. Push or pop a tag field for a VLAN or MPLS packet. The set field. The various set field actions are identified by their field type and modify the values of respective header fields in the packet. Lastly, the change TTL. The various change TTL actions modify the values of the IPv4, TTL, IPv6 hop limit, or MPLS TTL in the packet. So as to instruction components, action set is a list of actions associated with a packet that are accumulated while the packet is processed by each table and that are executed when the packet exists, and processing pipeline. The instructions are of four types: direct packet through pipeline, perform action on packet, and update action set, and the update metadata. Direct packet through pipeline, the goes to table. Instruction directs the packet to a table further along in the pipeline. The meter instruction directs the packet to a specified meter. Perform action on packet is actions may be performed on the packet when it is matched to the table entry. Update action set merge specified actions into the current action set for this packet on this flow, or clear all the actions in the action set. And then lastly, the update metadata. A metadata value can be associated with the packet. It is used to carry information from one table to the next. So it is the figure 21.9, packet flow through OpenFlow compliant switch. So here illustrates the packet flow. The packet in, then ingress port null action set into table 0, send packet to controller, drop packet, send to a flow table, group table, meter table, or direct to output port. Then packet ingress plus ingress port plus metadata plus action set to table K. Send packet to controller, drop packet. Send to the flow table, group table, meta table, or direct the output port. Then packet plus ingress port plus metadata action set to table N. Then send packet to controller, drop packet, and then packet plus action set, then execute action set, and then packet out. Switch includes one or more flow tables. If there is more than one flow table, they organize as pipeline. With the tables labeled with increasing numbers starting with 0, when a packet is presented to the table for matching, the input consists of the packet, the identity of the ingress port, the associated metadata value, and associated action set for table. The metadata value is blank and the action set is null. Processing proceed. So next is table 21.2, open flow messages. It's just the table to the open flow messages. Since it doesn't show, table is not clear, I'll just read it. The message and description, controller to switch, features, request the capabilities of a switch responds with a features reply that specifies its capability, configuration, set and query configuration parameters, switch responds with parameter settings, modify state, add, delete, and modify flow group entries, and set switch port properties. Then the read state, it collects information from switch such as current configuration statistics and capabilities. And then the packet out barrier, it directs packet to a specified port on the switch. Barrier request reply message are used by the controller to ensure message dependencies have been met or to receive notifications for completed operations. The rule request, set or query rule of the OpenFlow channel, useful when switch connects to multiple controllers. Then the asynchronous configuration, set filter on asynchronous messages or query that filter, useful when switch connects to multiple controllers. Asynchronous, packet in, transfer packet to controller. Then the flow removed, inform the controller about the removal of flow entry from a flow table. Port status, inform the controller of a change on a port. Error, notify controller of error or problem condition. Then the symmetry, symmetric hello, exchange between the switch and controller upon connection startup. The echo. Echo request reply message can be sent from either the switch or the controller and must return an echo reply. The next is the last one, the experimenter for additional functionality. So let's proceed for the mobile IP. Mobile IP enables computer to maintain internet connectivity while moving from one internet attachment point to another, particularly suited for wireless connections. Mobile implies a user is connected to one or more applications across the internet. The user's point of attachment changes dynamically. All connections are automatically maintained despite the change. So, it's the operation of mobile IP. Routers use the IP address in an IP datagram to perform routing. Network portion is used to move a datagram to the network the target computer is attached to. Final router uses the host portion to deliver to the destination. The mobile host, the IP address may change while one or more TCP connections are active. As next is the figure 21.10 mobile scenario. Here's the mobile scenario where we can find the home network. For A, the home agent, foreign agent, mobile node A, foreign network. We also have the server X, and in the middle, internet or other topology of routers and links. This figure shows in general terms how mobile IP deals with problems of dynamic IP address. A mobile node is assigned to a particular network known as its home network. Its IP address on that network, known as its home address, is static. When the mobile node moves its attachment point to another network, that network is considered a foreign network for this host. Once the mobile node is reattached, it makes its presence known by registering with a network node, typically a router, on foreign network known as foreign agent. The mobile node then communicates with similar agent on the user's home network known as a home agent, giving the home agent the care of address of the mobile node. The care of address identifies the foreign agent's location. Typically, one or more routers on a network will implement the rules of both home and foreign agents. So these are the basic capabilities of mobile IP. It is to support the operations illustrated in the last figure, which is mobile IP includes three basic capabilities. Discovery. Discovery procedure is used to identify prospective home agents and foreign agents. Registration. Authenticated registration procedure is used. And the tunneling. Forwards IP datagram from a home address to a care of address. So let's proceed to the figure 21.11. Is the protocol support for mobile IP. You can see the registration, discovery, and tunneling as what we tackled previously, which is the basic capabilities of mobile IP. In registration, user datagram protocol, and in discovery, there's a Internet Control Message Protocol, the ICMP. It indicates the underlying protocol support for the mobile IP capability. The registration protocol communicates between an application on the mobile node and an application in home agent, and hence uses a transport level protocol because registration is a simple request response transaction. The overhead of the connection-oriented TCP is not required, and therefore UDP is used as the transport protocol. Discovery makes use of the existing ICMP or the Internet Control Message Protocol by adding the appropriate extensions to ICMP header. Finally, tunneling is performed at the IP level. So let's proceed to table 21.3. The mobile IP terminology. Since it wasn't able to reflect the screen, I'll just read it. So we have the mobile node. Mobile node, a host or router that changes its point of attachment from one network or subnetwork to another. A mobile node may change its location without changing its IP address. It may continue to communicate with other internet nodes at any location using IP address, assuming link layer connectivity to a point of attachment is available. We have also the home address, an IP address that assigned for an extended period of time to a mobile node. It remains unchanged regardless of where the node is attached to the internet. Next is the home agent, a router on mobile node's home network that tunnels datagrams for delivery to the mobile node when it is away from home and maintains current location information for the mobile node. Next is the home network, a network possibly virtual, having a network prefix matching that of a mobile node's home address. Note that standard IP routing mechanisms will deliver datagrams destined to a mobile node's home address to the mobile node's home network. And we have the foreign agent, a router on a mobile node's visited network that provides routing services to the mobile node while registered. The foreign agent detunnels and delivers datagrams to the mobile node that were tunneled by the mobile node's home agent. For datagrams sent by a mobile node, the foreign agents may serve as a default router for registered mobile nodes. Foreign network, any network other than the mobile node's home network. The care of address. The termination of a point of a tunnel toward the mobile node for datagrams forwarded to the mobile node while it is away from home. The protocol can use two different types of care address. Foreign agent care of address is an address of a foreign agent which the mobile node is registered, and the collocated care of address is the externally obtained local addresses which the mobile node has associated with one of its own network interfaces. Correspondent node, a pair with which a mobile node is communicating. A correspondent node may be either mobile or stationary. Another one is the link, a facility or medium over which nodes can communicate at the link layer. A link either underlies the network layer. node, a host or a router. Tunnel, the path followed by a datagram while it is encapsulated. The model is that while it is encapsulated, a datagram is routed to a knowledgeable decapsulating agent which decapsulates the datagram and then correctly delivers it to ultimate destination. So the discovery is similar to the router advertisement process to define and define in ICMP. Mobile node is responsible for ongoing discovery process. Home or foreign network, it also listens for agent advertisement message. Compares IP address with home address. If these do not match, the mobile node is on foreign network. So we have the use of lifetime field. Upon receipt of an agent advertisement from foreign agent, the mobile node records the lifetime field as a timer. If timer expires before receipt of another advertisement, node assumes it lost contact. Otherwise, node uses agent solicitation to find an agent. If node has received an advertisement that is not expired, node registers with a new agent. So this is the use of network prefix. The mobile node checks if newly received agent advertisement is on the same network as the node's current care of address. If it is not, the node assumes it moved and registered with advertisement the node has just received. So next is the collocated address. Node may move to a network that has no foreign agents or foreign agents are busy. It may act as its own foreign agent by using a collocated care of address. And collocated care of address is an IP address that is associated with the node's current interface to a network. It can dynamically acquire a temporary IP address. Collocated address may be owned by the node. So the registration. Once care of address is acquired, the mobile node needs to request the home agent forward its IP traffic, and this is the registration process. Node sends a registration request to the foreign agent requesting forwarding service. Then foreign agent relays request to home agent. Home agent accepts or denies request, and foreign agent relays reply to node. If node is using a collocated care of address, it registers directly with its home agent. So next is the registration messages. Registration operation uses two types of messages carried in UDP segments. Registration request Message includes 1-bit flags, uh, home address field, home agent field, curve address field, identification field. And registration reply message includes acceptance code and the reason for denial. Next, the registration security. Mobile IP is designed to resist two types of attacks. Node pretends to be a foreign agent and sends registration request to home agent to divert traffic. Malicious agent may replay all registration messages, effectively cutting node from the network. And so the message authentication. Message authentication is used to protect against registration message attacks. Authentication extension includes the following fields: the security parameter index or SPI, an index that identifies a security context between a pair of nodes. This security context is configured so that two nodes share a secret key and parameters relevant to this association. Example authentication algorithm. And then the authenticator, a code used to authenticate the message. The sender inserts this code into the message using the shared secret key. The receiver uses the code to ensure that the message has not been altered or delayed. Authenticator protects the enter registration, request or reply message. Any extensions prior to these extensions and the type and length fields of this extension. It also has three types of authentication extensions. The mobile home. This extension must be present and provides for authentication of the registration messages between the mobile node and the home agent. Next is the mobile foreign. The extension may be present when security association exists between the mobile node and the foreign agent. The foreign agent will strip this extension off before relaying a request message to the home agent and this extension to a reply message coming from a home agent, and thusly the foreign home. The extension may be present when a security association exists between the foreign agent and the home agent. So next is the figure 21.12, a simple internetworking example. We can see the internet, the three LAN X, Y, and Z. We also have three routers, the router 1 to 3 and the hosts are the group members, group multicast, the A, B, C, and D. So here in figure 21.12, once a mobile node is registered with the home agent, the home agent must be able to intercept IP datagrams sent to mobile node's home address so that These datagrams can be forwarded via tunneling. The standard does not mandate a specific technique for this purpose, but reference ARP address resolution protocol is possible with a destination address to mobile node in question should be delivered and the link level to this agent. In effect, the home agent steals the identity of mobile node in order to capture packets destined for that node that are transmitted across the home network. So next is the figure 21.13 mobile IP encapsulation. We have the old IP header and the new IP header. Table 21.13. IP within IP, entire IP datagram becomes payload in new IP datagram. Originally, inner IP header unchanged except TTL decremented by 1. Outer header is a full IP header. And minimal encapsulation, new headers inserted between original IP header and original IP payload. Original IP header modified to form new IP header. The next is the dynamic host configuration protocol. Internet protocol that enables dynamic allocation of IP address to hosts defined in RFC 2131. It was developed to deal with the shortage of IP addresses. It enables a local network to assign IP addresses from a pool of available IP addresses to hosts currently in use. When a host is not in use, its IP address is returned to the pool managed by a DHCP server. It can also assign permanent IP addresses to some systems such as servers so that the address remains the same when the system is rebooted. Almost done. So here's the figure 21.14, the DHCP rule. Here in DHCP rule, DHCP operates on client-server model, with any host acting as client that needs an IP address upon booting up and a DHCP server that provides the request IP address along with related configuration parameters. The configuration parameters may include the network address of a default router for communication outside the local network and the address of a local DNS server. So next is the following DHCP messages are used for protocol operation. The DHCP discover, client broadcast to locate available servers. The DHCP offer server to client in response to DHCP discover with offer of configuration parameter. DHCP request client message to servers either A. Requesting offered parameters from one server and implicitly declining offers from all others, B. Confirming correctness of previously allocated address after, for example, system reboot, or C. Extending the lease on a particular network address. We also have the DHCP server to client with configuration parameters including committed network address, and then the DHCP NAC server to client indicating client's notion of network address is incorrect, like client has moved to new subnet or client's lease has expired. DHCP decline client to server indicating network address is already in use. DHCP server should then notify sysadmin. And we also have the DHCP release client to server relinquishing network address and canceling remaining list. DHCP inform client to server asking only for local configuration parameters client already has externally configured network address. Again, it is the figure 21.15 DHCP message exchange. It doesn't reflect again, so I'll just explain what happened. So from it is the relation of host and the DHCP database. So from host, so this figure 21.15 illustrates a typical message exchange. The following steps are involved. The client broadcasts a DHCP discover message on its local physical network. The message may include options that suggest values for the network address and lease duration. Relay agents may pass the message onto the DHCP servers not on the same physical network. Each server may respond with a DHCP offer message that includes an available network address. 3. The client receives one or more DHCP offer messages from one or more servers. The client may choose to wait for multiple responses. The client chooses one server from which to request configuration parameters based on the configuration parameters offered in the DHCP offer messages. The client broadcasts a DHCP request message that includes the server identifier option to indicate which server it has selected, and that include the other options specifying desired configuration values. This DHCP request message is broadcast and relayed through DHCP release agent. The client times out and retransmit the DHCP discover message if the client receives no DHCP offer message. Then the servers receive the DHCP request broadcast from the client. Those servers not selected by DHCP requests message used the message as notification that the client has declined that server's offer. The server selected persists selected in the DHCP request message commits the binding for the client to persistent storage and respond with DHCP pack message containing the configuration parameters for the requesting client. The next is the client receives the DHCP pack message with configuration parameters. At this point, the client is configured. And then, lastly, the client may choose to relinquish its lease on the network address by sending a DHCP release message to the server. So in summary, we have the multicasting with requirements for multicasting, the IGMP and the PAM, and we also have the hard software defined networks or the SDN. Under this is the evolving network requirements, the SDN architecture and the SDN domains. And then the another topic is dynamic host configuration protocol, the open flow. Under the open flow, we have the logical switch architecture, flow table components, flow table pipeline, open flow protocol, and lastly the mobile IP. It has the operation of mobile IP, the discovery, the registration, and the tunneling. And that's all. End of the report. Thank you, everyone.